Think about the last time you bought something online, right? You probably looked up at the URL bar, saw that little padlock icon, felt this subtle sense of security, and just confidently hit purchase. We all do it.
Yeah, we really do.
But here is the unsettling reality about that. That little padlock only secures the tunnel your data travels through. It protects your credit card while it is in transit. But what happens when your data actually reaches its destination? Like, what is actually sitting on the other end of that tunnel?
Well, it is a massive, incredibly complex piece of software called a web server. And the second your private data exits that secure tunnel, it is entirely at the mercy of that server's architecture, its configuration, and frankly, the competence of the person who set it up.
And that is exactly what we're getting into today. Welcome to the Deep Dive. Our mission today is to pull back the curtain on these invisible engines that run our digital lives. We're going to explore not just how web servers actually function, but exactly how they break.
Right, because we want to understand the incredibly ingenious ways attackers exploit them.
Exactly. And what the cybersecurity professionals are doing to patch the holes before your data gets stolen.
Right.
Because every single time you open a browser, you are placing your entire digital identity in the hands of this infrastructure.
It is a huge amount of trust. And while we often have this Hollywood image in our heads of hackers as like brilliant hooded masterminds breaking unbreakable encryption with a flurry of keystrokes, the truth is far more mundane.
Oh, completely.
Yeah, I mean, massive corporate networks are compromised every single day by things that would shock you. A lazy default password, a misconfigured file folder, an error message that basically hands the attacker a blueprint of the entire system.
Okay, let's unpack this. If we are going to understand how these systems are breached, we really need a solid mental model of what a web server actually is. I like to think of a web server as a massive, highly efficient restaurant.
Oh, I like that. That is a great baseline. Let's build on that. So in web server architecture, you generally have two main distinct areas. The first is the document root.
Right, so in our restaurant, the document root is the public dining area and the menu. It is exactly where the customers, the web clients who are, you sitting at your laptop are supposed to be.
Yep, exactly.
You look at the menu, you request a specific web page, and the server's job is to go fetch it and bring it out to your table.
Precisely. Which brings us to the second area, the server root. This is the kitchen, the manager's office, the back room where the safe is kept.
The places you definitely do not want customers going.
Right. This is where the core configuration files, the system logs, and the executable scripts actually live. And the golden rule of web server security is that a customer from the dining room should never, under any circumstances, be allowed to wander into the kitchen.
Right. But running a global restaurant that serves millions of customers a second requires some serious infrastructure. And in the real world, the vast majority of the internet is powered by what we call the big three web servers.
Right. Nginx, Microsoft ICE, and Apache.
Yeah, and they each build their restaurant very differently. And because of that, they each have their own unique structural flaws.
So let us look at Nginx first. Nginx was built fundamentally for pure speed and handling massive traffic spikes. To do that, it uses something called a master worker architecture. You have one master process that manages the overall configuration, but the actual heavy lifting of serving web pages is handed off to multiple worker processes.
And the key here is that they operate asynchronously, right?
Yes.
Which means a single worker process can juggle thousands of customer requests at the same time without waiting for one to finish before starting the next.
It is an incredibly efficient, non-blocking model, but, that specific design choice introduces specific vulnerabilities. Take something called a NALL pointer dereference.
Okay, I'm going to need you to translate that one. NAL pointer dereference sounds like something from a computer science final exam.
Fair enough. Think of a pointer in programming as a set of directions to a specific house where some data lives. Now imagine a worker process is handed a set of directions, but the address is blank. It points to NUL, to absolutely nowhere.
Oh, I see.
Yeah, when the worker tries to go to that blank address to read the data, the operating system panics and immediately crashes the program.
Wow. So If an attacker figures out how to intentionally send a maliciously crafted web request that forces the server to look at a blank address, they can deliberately crash that worker.
Exactly. And because Nginx relies on those workers juggling thousands of requests asynchronously, crashing them, or flooding them with complex HTTP2 requests that exhaust all the server's memory, creates a massive denial of service.
Right.
The server is so busy trying to process the junk or recovering from crashes that legitimate users get locked out.
Okay, so that is Nginx and its asynchronous model. Then you have Microsoft ISIS, which takes a completely different path. ISIS is deeply integrated into the Windows operating system itself.
Yes, it is.
It is not just an app running on the computer. Its roots go all the way down.
This is a crucial distinction. ISIS relies heavily on core Windows components. It uses a protocol listener called http.sys.
Okay.
And http/sys does not just run as a normal program, it sits right in the kernel mode of the operating system to intercept web requests as fast as possible.
But hold on, the kernel.
Yeah.
Isn't the kernel the core brain of the operating system that controls everything? Like hardware, memory, security. Putting a web listener, something designed to talk to the wild, untrusted internet directly into the kernel, seems incredibly risky.
It is a massive trade-off for speed. Microsoft does it because processing requests at the kernel level is blisteringly fast. But you're absolutely right about the risk. Because it sits so deep in the system, when a vulnerability is found in ISIS, it often looks like an operating system flaw.
Ah, I get it.
You see things like elevation of privilege vulnerabilities.
Meaning, an attacker does not just compromise the website, they use that kernel-level access to elevate their permissions and basically become an administrator of the entire server machine.
Exactly. They manipulate specific user requests to gain unauthorized control over the whole Windows environment, not just the web folder.
That is terrifying. Okay, so that brings us to the third giant, Apache. Apache is the granddaddy of open-source web servers. Its whole philosophy is modularity.
Right, like building blocks.
Exactly. You only install the specific modules you need to customize your server.
It is incredibly flexible, but every module you add is a new piece of code written by different people interacting in complex ways. And that brings us to things like buffer overread vulnerabilities, specifically in modules like mod macro.
Let us break down buffer overread. A buffer is just a temporary storage box in the computer's memory, right?
Correct. Imagine the server allocates a little box in memory to hold the data you just submitted, maybe a search query. But because of a flaw in how the module checks the size of your input, an attacker can trick the server into reading past the end of that specific box and into the adjacent memory.
And what is sitting in that adjacent memory?
That is the jackpot. It could be anything. It could be another user's session cookie, an administrative password, or private encryption keys. The attacker is essentially reading the server's private diary just by overflowing their own designated memory box.
Wow. So hearing all this, open source consortiums, massive enterprise backers, they have endless funding, and the smartest engineers in the world. Why are they still vulnerable to things like memory overflows or simple logic flaws?
What's fascinating here is that their greatest strength is inherently their greatest weakness. The reason Nginx, ISIS, and Apache are everywhere is because they are flexible.
Right, they have to do everything.
Yeah, they cannot just serve plain text files anymore. They have to integrate with complex databases, run dynamic scripts, handle video streaming, and support thousands of third-party plugins. Every single time you add a new feature or a new capability, you expand the attack surface. In cybersecurity, complexity is the absolute enemy of security.
That makes total sense. The bigger the restaurant, the more doors and windows you have to guard. And because these architectures are so sprawling and complex, attackers have moved way beyond just trying to guess a password. They have developed some truly ingenious methodologies.
They absolutely has, and sometimes they do not even bother attacking the server directly. They attack the infrastructure around it. Let us look at DNS.
Right, DNS, the domain name system. It is basically the internet's GPS. Humans remember words like mybank.com, but computers need numbers, IP addresses. DNS translates the words into the numbers to route your traffic.
Right.
And attackers can manipulate this GPS system in two major ways. First is DNS hijacking.
This is a direct attack on trust. The attacker compromises a DNS server and literally alters the map. Yeah, you type in your bank's legitimate URL. Your computer asks the compromised DNS server for the location, but the server silently gives you the IP address of the attacker's fake, identical-looking website.
So you land on a page that looks exactly like your bank, you type in your password, and boom, They have your credentials. You never even reach the real web server. But the second DNS attack, DNS amplification, operates on a totally different logic.
It does.
It is not about stealing data. It is about crushing the target.
It is a brilliantly devious form of a distributed denial of service, or DDoS attack.
I love the mechanics of this one. To use an analogy, imagine I want to completely overwhelm someone's house with junk mail, but I do not want to carry it all myself.
Okay.
So I take a tiny, lightweight postcard, and I write their address as the return address. Then I send thousands of these little postcards to warehouses all over the country, requesting their biggest, heaviest catalogs.
And the warehouses receive the tiny request, process it, look at the forged return address, and ship thousands of massive, heavy catalogs directly to your victim.
Exactly. In the digital world, an attacker uses a botnet, a network of infected computers, to send millions of tiny, lightweight DNS queries to open DNS servers across the internet. But they spoof the source IP address to make it look like the request came from the target web server.
Right. So the DNS servers process all those queries and send the massive, amplified responses back to the spoofed address. The target web server is suddenly hit with a tsunami of unwanted data it never asked for, completely drowning its network connection.
It is asymmetrical warfare. The attacker uses a tiny amount of effort to trigger a devastating wave of traffic.
Exactly.
But let us move from attacking the map to actually sneaking inside the building.
Right.
One of the most classic exploits is directory traversal. Going back to our restaurant, this is the customer actively trying to pick the lock on the kitchen door.
It is surprisingly common, honestly. Web applications are supposed to restrict you to the document route, but if an application does not strictly validate the input a user types in, an attacker can use a very simple old-school sequence of characters, ..
It seems almost too simple to work on modern systems.
You would think so. But in almost all operating systems, .. is the universal command to move up one directory level. So imagine a URL that ends with image equals logo.jpg.
Okay.
The attacker deletes logo.jpg and types in .. //windows/system32/cmd.fce.
So they are literally telling this server, take a step back, take another step back, go out of the public folder, walk up the directory tree, into the restricted operating system files, and hand me the command prompt.
Exactly. They traverse the directories. If the web server is running with administrative privileges, which it often is due to bad configuration, it blindly obeys the command and hands the attacker the keys to the kingdom.
Here is where it gets really interesting, though. There is an exploit called HTTP response splitting. And this one requires a deep understanding of how web traffic fundamentally works.
It really does. When your browser talks to a server, it uses HTTP, which is essentially just structured text. The server sends back a text response, and at the very top of that text are headers.
Right.
Headers are hidden instructions for your browser. Things like set this cookie or redirect to this page.
And those headers are separated by invisible formatting commands, specifically carriage return and line feed, basically the enter key.
Yep.
In response splitting, an attacker finds a vulnerable input field like a search bar that gets reflected back in the page, and they inject those exact carriage return and line feed characters into their search.
And this is where the magic happens. The web server reads that input, sees the injected enter key commands, and mistakenly believes the current header has ended and a completely new response has begun. The attacker literally tricks the server into splitting a single response into two separate responses.
And the brilliance of this is that the attacker has meticulously crafted that newly created second response. They control the content. They can insert a header that redirects the user to a malware site, or inject a script that steals their session token. The user's browser processes the attacker's fake response and entirely ignores the real data that follows it.
And if we connect this to the bigger picture, it gets even worse when you introduce web cache poisoning.
Yes, because to make the internet fast, intermediate servers constantly cache or save copies of popular web pages.
Exactly. So if an attacker uses response splitting to force a server to output their malicious crafted response, and that response gets scooped up and saved by a caching server,
then every single legitimate user who visits that URL afterward does not even talk to the main server. They get served the poisoned, infected content directly from the cache.
The attacker exploited the system once, but the internet's own optimization tools distribute the malware to thousands of people automatically.
It is completely wild. Now, we have just spent a lot of time talking about highly technical exploits, memory buffers, header injections, asynchronous crashes. But a massive takeaway here is that attackers really have to sweat that hard. Because more often than not, a human administrator just leaves the front door wide open.
Oh, absolutely. The human element will always be the weakest link in any security chain. Administrators are under immense pressure, constantly balancing competing priorities. If you look at it from different perspectives within an organization, you see why web servers are inherently risky.
Let us break down those perspectives. First, you have the webmaster.
Right, so the webmaster lives in a state of anxiety because a web server is essentially a bridge. It connects the hostile wild internet directly to the company's internal local area network.
Right.
It has to be public to serve customers, but if it gets breached, it becomes a beachhead. Attackers use it to pivot and launch deeper attacks into the private corporate network.
Then you have the network administrator. They are dealing with an impossible equation. Their mandate is to keep the network absolutely secure. But if they lock down the server with too many firewalls, complex authentication, and strict access controls, the web server becomes so slow and cumbersome that employees and customers cannot actually use it. Security and usability are always at war with each other.
And then there's the third perspective, the end user, you and me. When we browse the web, we generally feel safe. We do not realize that modern web servers are not just sending us text anymore.
Yeah, that is a huge shift.
They are pushing advanced active content complex JavaScript WebAssembly directly down into our browsers for our local machines to execute. And users blindly trust this pipeline, not realizing it is a massive open pathway for malicious code to run directly on their personal computers.
And because of all these competing pressures, like the need for speed, usability, and complex features, the humans managing these servers make mistakes. The list of common misconfigurations is honestly staggering.
It really is. One of the most devastating is simply reusing system administrator credentials.
Oh, the classic password reuse.
Yep. An attacker finds a minor vulnerability on some forgotten low-priority staging server, extracts the password, and suddenly they have full access to the primary financial database because the admin used the exact same password for convenience.
Or what about verbose error messages? This one blows my mind. You have a configuration setting, say in PHP, where displayer is set to cur. It seems helpful for the developers when they are debugging the site.
It is helpful for developers, but it is a goldmine for attackers.
Right.
If an attacker intentionally feeds the server garbage data to force a crash, instead of a generic, oops, something went wrong page, the server spits out a highly detailed diagnostic report.
It literally says, here's the exact version of the database we are running, here is the specific line of code that failed, and by the way, here is the entire internal file path structure of our hidden directories.
You are handing the attacker the architectural blueprints to the vault. It is reconnaissance handed over on a silver platter.
Wow.
Another massive human error occurs in Nginx configurations with missing root location blocks.
Right. What does that do?
If an administrator forgets to properly define the boundaries of the document root, it can trigger undefined behaviors where the server gets confused and accidentally exposes a complete directory listing of sensitive internal files to anyone who asks.
So when a human error like that happens, and the attacker walks right through the open door, what is the actual fallout?
The impact scales from embarrassing to catastrophic. At the most visible level, you have website defacement.
Yeah, we have all seen this. You go to a corporate homepage, and instead of their products, it is a black screen with a skull and crossbones and massive neon text screaming, "You are owned," hacked by some group.
It looks like a digital prank, but the business impact is severe. It is a massive reputational nightmare. You are broadcasting to every single one of your customers in real time that you are completely incapable of securing your own systems.
And defacement is usually just a distraction, right?
Often, yes.
While everyone is panicking about the homepage, the attackers are going for root access. If they get root privileges, they own the server. They can quietly alter financial records, modify databases, or execute their ultimate goal, data theft, pulling thousands of credit cards, user passwords, and proprietary source code right out the back door.
Which ultimately leads to the destruction of the company's reputation. If your customers lose faith that you can protect their most sensitive data, the business is effectively over.
So what does this all mean for the defense? Given the structural flaws we talked about in Apache and ISA, the complex exploits like cache poisoning, and the inevitable reality of human error, How do cybersecurity professionals actually fight this? It sounds impossible.
It is a monumental task, and the only way to manage it is through aggressive automation and rigorous, almost militant discipline. You simply cannot secure a modern web server manually.
So they rely on automated scanners. Tools like Scyhunt Hybrid, which is specifically designed to constantly crawl a company's website, automatically generating signatures to detect JavaScript vulnerabilities or hidden cross-site scripting flaws.
Right.
Or they use deep penetration testing tools like Core Impact.
Exactly. Core Impact is fascinating because it mimics the actual behavior of advanced cybercriminals. It actively tries to exploit the system in a controlled way to evaluate the real-world security posture of the server before the actual bad guys find the hole.
But scanners only tell you what is broken. They do not fix it. The real defense comes down to patch management, which brings up a terminology question. What is the actual practical difference between a hotfix and a patch?
Yeah.
People use them interchangeably all the time.
They're very different in practice. A hotfix is a frantic emergency repair. A vendor discovers a critical zero-day vulnerability that is actively being exploited in the wild. They rush out a hotfix to plug that specific hole immediately. It is putting out a fire.
Okay, and a patch.
A patch is a broader, scheduled software update. It is thoroughly tested by the vendor and designed to fix multiple bugs, update features, and improve overall stability.
But applying those patches is never as simple as just clicking Update all on your iPhone. In a massive enterprise environment, there is an entire automated patch management cycle.
It is a relentless, continuous loop. First, you detect. You use scanners to inventory your network and find exactly which servers are missing which security patches. Then you assess. Is this vulnerability actually relevant to our setup? How severe is it? Then you acquire the patch securely from the verified vendor.
And the next step is the absolute golden rule of IT test.
Yeah.
You never, ever deploy a patch to a live production server without installing it on an isolated test machine first.
This cannot be overstated. Sometimes the cure is worse than the disease.
Oh, for sure.
A security patch might successfully plug a vulnerability, but in doing so, it might completely break a custom application that your business relies on to function. You have to know what the patch will break before you roll it out.
Right. So after rigorous testing, you deploy it to the active network, and finally, maintain. You track the installation to ensure it actually took effect everywhere, and you always have a rollback plan ready in case a deployed patch causes catastrophic, unforeseen issues on the live server.
It requires incredible discipline. In a network of 1,000 servers, one single forgotten machine missing one critical patch can be the entry point that brings down the entire global network.
Wow. Okay, so synthesizing everything we have covered today, we started by looking at the invisible engines of the internet. We saw how the fundamental architectures of Jinx, IS, and Apache, their need for speed and modularity create complex structural vulnerabilities. We explore the ingenious ways attackers exploit that complexity, from forging DNS postcards to flood a server to injecting invisible carriage returns to split HTTP headers and poison the cache.
And we grounded all of that in the reality of human error, how reused passwords and verbose error messages often render all that sophisticated hacking completely unnecessary.
Which is exactly why the relentless discipline of automated scanning and rigorous, tested patch management is the only thing keeping our digital ecosystem functioning.
It is a never-ending arms race.
It truly is. Now, before we go, I want to circle back to something we touched on earlier, a final thought for you to mull over. We talked about the end-user perspective, how surfing the web feels safe and anonymous.
This is where the landscape is really shifting. Modern web servers are incredibly burdened. To save their own computing resources, they are increasingly offloading the heavy processing work onto our personal machines.
Right. They're not just sending you a static picture of a web page anymore. They are pushing highly complex, active, content-intricate WebAssembly routines, massive JavaScript frameworks directly down the pipe into your browser. It is your laptop's CPU that is actually executing all of that code.
And this raises an important question. If a massive corporate web server is pushing its own operational logic onto your personal device for execution, where does the corporate server actually end and your private computer truly begin?
It is a wild thought. If your browser is doing the heavy lifting and executing their code, aren't you, in a very real way, becoming a temporary distributed extension of their server architecture? The next time you see that little padlock icon, remember, the data is not just sitting securely in a remote vault somewhere. A piece of that machine is running right there on your desk inside your browser, and the door might just be wide open.